Okay, we're back. This is the third in a set of videos about, I should have shown my little title slide. Let's see here. Here we go. Modal analysis, modal frequencies and mode shapes. So, where we were, I'll put my Word file up here. And then I told you that, well, there's Octave, which we use, but I found a way to blow it up. Where did it go? Here we go. Another good old open source program, Notepad++, just for text editing. These are the commands that I entered in. Here you can see how I made my mass matrix. Here's my stiffness matrix, and those all came from this formulation right here. Okay, let me get it back. I was going to invert the mass matrix, so I wanted to check it first to make sure that it was invertible, although I was sure that it was. But I certainly did get a number that was not 0, which means that I can invert it. And then my eigenmatrix, the one that's going to contain the eigenvectors and eigenvalues and eigenvectors, is the matrix counterpart to the single degree of freedom system relationship omega n squared is equal to k over m. So this is k over m basically in matrix format. And then I get this eigenmatrix here. And then I try to actually get the eigenvectors and eigenvalues just by issuing the eigs function on the eigenmatrix. But that didn't work. I got the eigen values, but I didn't get the eigenvectors. So with this formulation here, I've done this before, so I knew how to do it. I didn't have to look it up, but you can look it up in Octave also. Let's look at first the eigenvectors are a little bit more complicated than the eigenvalues. So let's look at the eigenvalues first. So these are our natural frequencies squared. Okay, the values on the diagonal. Okay. So I really don't like the fact that they give them in what I consider to be the wrong order. You should give the lower order frequencies first, and then the lowest frequencies first, and the higher frequencies second. But Octave delivers them this way, and we just have to live with that. So interesting is that our first natural frequency is 0. Okay. Now, whenever you see a 0th order natural frequency, what that means is that that's rigid body motion. You don't have any spring flexibility or whatever, and I'll talk about what that means in just a second. Our second natural frequency is actually the square root of 2. Remember that the eigenvalues are the square of the natural frequencies, not the natural frequencies themselves. So our two natural frequencies are 0 and square root of 2 radians per second. Now, let's look at the eigen vectors, and these are also given in the order that the eigenvalues are given in. They're consistent with that. So let's look at the lowest order mode first, but before I do that, what I need to tell you, this is one eigenvector here. They're in columns, and here's the second eigenvector here. The eigenvectors, the value of each component of the eigenvector is actually not that important. It's the relative value of the two that's important. So this is one possibility here. Notice that these are the same. What that means is that if you this is going to quote unquote oscillate with this type of eigenvector. Now, since they're the same, this doesn't necessarily mean that the value of the amplitude is 0.70711. It's the comparison of these two, and the fact that they're the same says that whatever the displacement of the first mass is, the second mass is going to be the same displacement. So I can actually multiply these by whatever I want to, as long as I multiply by multiply both by the same constant. Okay, so if I move so the first mode is if I move the first mass to the left 0.707, 11, or whatever value, the second mass is also going to move to the left by that same amount, or at least that's the vibration mode of this system. And what that means, obviously, since you're not going to be stretching the spring, is you're not going to have any oscillation at all. And we'll see that in just a second. Now the second mode is a little bit more complicated, and that's what happens, as we saw. The higher up you go in mode shapes, the stranger they get, I guess you would say. We only have two mode shapes here, not an infinite number, because we only have, we're looking at a lump mass system, and the number of mode shapes is equal to the number of masses that you have. But look at what's happening here. The first mass, so let's go back. Look, they're the same number, but they're opposite in sign. And the first one is negative, the second one is positive. Now, I could multiply this by -1 and have this be positive and have this be negative. That is legal with mode shapes because, like I said, it's not the number, the size of the component of that piece of the mode. It is the relative size of the two. So basically, what this says, all it says, is it says in the second mode, I'll move the first mass to the left by the same amount that I move the second mass to the right. Or, if I multiply this by -1, this would be positive and this would be negative. And then it would be saying, so if this were positive and this were negative, because I multiplied by -1, if I move the first mass to the right, the second mass will move to the left by the same amount. So let's go look at our picture. And what's going to happen here is with the first mode shape, now they were negative, and I have to the right being positive. If I move this mass to the left by a certain amount, and I move the second mass to the left by exactly the same amount, and I let them go, what are they going to do? Nothing. And that complies with the modal frequency for that mode shape. They're not going to oscillate. They have a modal frequency of 0. Okay? Now the second mode is interesting. If I move the first mass to the left and I move the second mass to the right by the same amount and I let them go, what's going to happen is that these are just going to bounce back and forth away from each other and then towards each other. Okay? And they will do it at a natural frequency of square root of 2 radians per second. Okay? Now, I can show that in Octave too. And I'm not going to type up the files for doing this because I've already done them. Let me see if I can pull them up real quick. Yeah. Double mass not fixed. So I'll show how these were done. And actually, I think I can blow these up. Once you get you're editing a file, I think you can blow it up. So double mass not fixed. Yeah, that worked. So let me get us a little bit more room here. All right, come on, behave. There we go. So this is two masses, M1, M2. Oh, I have different values here. I could actually put our values in. In fact, I will. Let's just modify this. So I think I had 10,000 here. No, sorry, I don't need that extra 1. I hope this works because I haven't done this yet. I did this other system. Okay, and then we had a K12 of 10,002, so everything's 10,000. But basically what I've done is I formed the state space version of my system, and I don't know if I've talked about that elsewhere, but basically what you do is you have two first order systems and you need to convert them into, so that's two first order systems with or second order. You need to convert that into an overall system that has 4 first order derivatives in it. And I'm not going to cover that now. Maybe I will later on in a video, but you can look up state space formulation and see how to do that. Or look here for a video produced at a different point where I show how to do that. So let's go back to Octave and to my, actually what I'm going to do is stop again. We'll start back up here again. Let me stop and we'll start back up here with the next video.